Very happy to be back in Toronto. I spent that last week in Washington, D.C., and that town is crazy right now. I'm so happy to be back in Canada. How were the guest lecturers? Pretty good? Yeah, they did all right? Okay, very good. Yeah, happy to hear it. So we're going to continue on with the stuff. There's a couple things I want to advertise. So regarding our course, there's a new set of recommended exercises. So if you go to MATB41, there's a new set of suggested exercises available here. Okay, so this is the new list for the second half of the course. So if you printed off the list for the first half of the course from the syllabus, I recommend printing off this list and going through it. So that's available online now. I highly recommend that. Okay. The other little advertisement that I have is I'm going to be giving a public lecture this Friday. So it's going to be here at U of T on some math, not related entirely to our course, but if you want to learn more math, and especially if you're interested in taking any third year or fourth year courses, this will be a fun public lecture to come to. So that's this Friday, 11 a.m. in IC 200. Okay, so if you like, yes?
What kind of stuff will you be going over?
So we're going to, okay, so here's the topic of the lecture. So we know what it means for a list of numbers to converge to a value, right? So we know what it means to say the sequence xn limits to L, right? That's good, we've got that. But what does it mean for a sequence of functions to converge to a function? Okay, so we've talked about these infinite series, and we say that they approach some limit. How do they approach it? So we'll get into those details. Sequences of functions. Okay, so that'll be the topic there. Very good. Okay, are there any questions or thoughts coming up for people? Questions or thoughts? Okay, very good. Right. Oh yes, so I had a question for you guys. So what do you know about second derivative test? So okay, so this was the topic of Ray's lecture last Thursday, and I just wanted to know how far you guys got. So if anyone's got a theorem statement or a main example, that'd be very helpful. Yeah, maybe talk with your neighbor for a moment, see if you can figure out where you got to with second derivative test last Thursday. Yes, over here. Oh, we didn't reach it. Oh, okay, very good. All right, so that's what we're going to do today then. Awesome. So you guys talked about critical points, right? You talked about critical points. Okay, we say that a particular value is a critical point. Of a function if it's not differentiable at that point, or the gradient at that point is equal to 0. Okay, so what's this second condition mean? So Ray, in his lecture, might have written out the following statement. Right? We can also say that something's a critical point if the partial derivatives vanish. Okay, so that's familiar from last lecture. Could I get a show of hands? Yes, it's familiar. There's like 3 people. Yes, okay, great. Cool. So we've got that. That's familiar. Okay, so we're going to go from there to stating our second derivative test. So we have to recall how second derivatives work. How to calculate critical points, etc. Okay, so in one variable, we can classify mins or maxes in the following way. Okay, if the second derivative at a critical point is 0, then we're a max. And then we're a min. Okay, so the way that I always remember this particular theorem in single variable calculus is by drawing the following figure. Okay, so here's x squared. Here's negative x squared. And in this example, we've got that our second derivative is always equal to 2. And here we get our second derivative is always equal to negative 2. Okay, so the sign of the second derivative matters a lot here. Right? If we're positive, then we get a min. If we're negative, then we get a max. Okay, so now we want to generalize this to multiple variables. Okay, so what should our analogy be for the second derivative if we have multiple variables? Right, what's the sort of the best analog for the second derivative? It should be the matrix of second derivatives, because we've got many, many of them. All right. Our analogy for the second derivative is something called the Hessian matrix, and it says the following thing. Okay, so we take the derivative in xi, and then we take the derivative in xj. Okay, so that matrix of second derivatives will play the role of f prime prime for us. Okay, so let's see how to calculate a Hessian matrix. Okay, so we'll find the Hessian of x squared plus y squared. That's kind of our analog for the function x squared. This is sort of a two variable version of the function x squared. Okay, so we apply the definition. Now we'll compute each of the first derivatives. Okay, and we're going to get the following thing. We're going to get 2, 0, 0, 2. Okay, so that's very much like our second derivative of this function. Okay, and I want to do a similar example, but now we'll put negatives out front here. Okay, so take a moment, calculate this out. Okay, so here the calculation will go through very similar to what we had before, except now we'll carry around these negatives everywhere. Okay. So we see sort of similar things as we saw with the x squared and negative x squared. We see that we get these negative signs coming up. Okay, very good. Okay, so now let's do something with a bit more complicated structure. Okay, so let's find the derivative or second derivative and evaluate it at a point. Whoops. Sorry, let's switch the point. Okay. Oh. So when calculating the Hessian, it helps to get the first derivatives first. right? And then from there, we can calculate out the second derivative. Zero. Like this. And now we put in our point. And we get something like this. Are there questions or thoughts about that setup? Okay, so that's the Hessian for a two-variable function. Okay, now I'd like to talk a little bit about maxes and mins so that we can start getting towards this second derivative test. Okay, we say that this is a local something is a local maximum if it is bigger than all the values nearby. Okay, so we say that something is a local maximum if it's bigger than all the values that are near to it. All right, so this word near is a little bit imprecise. What we want to say here is something like there is an epsilon so that if the distance between y and c is less than epsilon, then this happens. And that's one way of saying near. Okay. So local means that this happens for some small value, so for values nearby. Okay, we say something is a local minimum if we get the reverse inequality. Okay, so this is smaller than all the values nearby. Okay. So a key fact for us is going to be the following. Okay, if we are differentiable near C, and that value is a local min or max, then the gradient at that point will be 0. Okay, alternatively, alternatively, this thing is a critical point. Okay, why should this fact hold? Why is this true? Right? If we had a gradient that wasn't equal to 0, what could we do? Yeah, over here. Yeah, we could increase further. So if the gradient was not equal to 0, oh, sorry, this should say with C. If the gradient is not equal to 0, then we can increase or decrease our function by following the gradient. Okay, so if we're differentiable at a critical point, then our gradient will be 0. Okay, great. All right. So now I'd like to get into the details about how to figure out if a critical point is a min or a max. So there's our Hessian. There's our one variable example. Okay. So there are two examples I'd like you to keep in the back of your mind. Okay, and these are the 3D analogs of these two examples here. Okay, so for this function, we're going to call this a cap. Okay, the idea is that it's sort of like a hat. You know, you could take this parabola and put it on your head as a really weird Halloween costume. And then the other example is this cup. Okay. Yeah, sure.
The diagram of the cap, should the axes be switched?
Oh yes, sorry, they should totally be switched. Yes, thank you. X, Y. Good. Sweet. Okay, so these are sort of the 3D versions of the graphs we just had. Okay, and I want to draw your attention to the gradient of these, or sorry, the Hessian matrix for these guys. Here we have our Hessian is 2, 0, 0, 2. Here our Hessian is like this. Okay, so what's interesting about both of these matrices is that they both have the same determinant. right? They both have determinant 4. Okay, so we can't figure out whether we're a cup or a cap just based on determinant alone. Okay, there's one other sort of key example of a function. So our last example of a function before we can state the second derivative test is this guy here, where we have a minus sign just on one of the terms. Okay, here we get one negative sign in one direction and a positive sign in the other direction. Okay, this graph is very hard to draw, so I won't draw it, but I'll draw its contour plot for you. Okay, so the contour plot of this will look something like this. Okay, so we'll get red lines when it's positive. And blue lines when it's negative. Okay, so I've left the computer on so that we can see what this thing looks like sketched in 3D. Okay, so we've got this, this last key example of a function. Let's see what it looks like plotted in 3D. Okay. And it looks something like this. Okay, one sec. Maybe I'll... helps a little bit. Okay, so what we can see is for half of the graph, it's positive. That's this stuff here that we're drawing in red. And then for the other half of the graph, it's negative, which we're drawing in blue. Okay. And we can see that in one direction, the graph is sort of like a parabola upwards, right? And if we look at it rotated 90 degrees, we see that it looks like a parabola downwards. So what's up with the critical point at 0 here? Is it a max or is it a min? Right? I think I heard a neither, right? It is neither a max nor a min, because if we go in this direction, we wind up going negative, and if we go in this direction, we wind up being positive. Okay, so this will be our sort of our third example of a two-variable function, and we're going to call this a saddle. Okay, the idea is that What's the best angle on this thing? Yeah, I guess the idea is that if we put our legs here and here, we could sort of sit on a saddle, okay? Another nice way of graphing this function that gives you a bit more physical intuition is if you hold your arm here, in one direction it's negative down, and in the other direction it's positive up. So you can imagine sitting on that sort of like a saddle. Okay, very good. So that's our third example that we'll use for defining our second derivative test. Okay, very good, the saddle. Okay, do we need this? Yeah, let's keep it up because we might graph one more thing. Okay. Good. Oh. Okay. So now we've got all the examples that we're going to need to state our second derivative test. Okay, so given a function which is differentiable near a critical point, we want to know which of the following three things happens. Okay. So in our three examples, we see that these two guys both have a positive positive determinant, right? And here we have a negative determinant. Here we'd have determinant -4. Okay, so we're going to say if the determinant is negative, then we get a saddle. If the determinant is positive and the second derivative here is positive, then we get a min. And we get a max. Okay, so these three examples sort of build the theorem for us, right? This example is where we have a cup, and this example is where we have a cap. Yes?
Does it have to be fxx and use fyy?
Ah, that's a great question. Yeah, can we switch fxx with fyy? So I guess we need to understand what that part of our theorem is doing for us, right? So here, both of these guys have positive determinant, right? So the first part of our theorem can't distinguish these, right? These two guys, whoops, sorry, this should be positive. Okay, so in both the cup and cap example, we have positive determinant. Okay, so what the fxx term is doing is it's focusing our attention on this entry here. And what that corresponds to geometrically is applying the second derivative test from one variable in the x coordinate. So we go here. We cut our shape along the x-axis. And we get something that's concave up. Okay, here we cut our shape along the x-axis. Right, and we get something that is concave down. Okay, and if we can cut it in one direction and we see that we get a max, then the original point had to be a max. If we can cut it and get a min, then the original thing had to be a min. So these terms are doing the single variable second derivative test for us. Okay, so that's the explaining what it's doing. And we could just as well cut in the y direction. Okay? Yes, sure?
So if the determinant equals 0, then we can't say anything?
Yeah, then it's inconclusive. Right. Yes. So then we get no conclusion. Yep.
What if the determinant is greater than 0, but x-axis is less than 0? What do we get?
Right. So if this thing is negative, then you're immediately a saddle. No further tests required. So if you're in this case, if you're less than 0, then no further tests required. Hmm? So here it's the determinant of the Hessian matrix. So we take the Hessian matrix, we put it in here, we get a negative number, then we're a saddle, no more questions. Yeah? Does that help? Cool. Sweet. Yes?
What if x-axis is also 0?
Right. Right. So if any of these things don't happen, then it's inconclusive. Right? So if you get something equal to 0, inconclusive, you don't know. So I just want to show you a geometric example of what this looks like so you have a sense of how this arises. Okay. So we'll find and classify the critical points of this. Okay. So we want to solve, to start off, right, find the places where this zeroes out. Okay, so these guys will both be equal to 0. When y is equal to negative x. So now we have a whole line of critical points. Right? There's infinitely many critical points that live along that line. Okay. And now we'll try and classify them using our second derivative test. Right, so we take the first derivative and get the stuff we need for the second derivative. Okay, so we write down our Hessian matrix. And we wind up getting no conclusion here. Okay, so this is a difficult place to be. The test didn't help. Okay, so now I want to point out the following geometric way of classifying them. Okay, looking back at our original function, right, we see that this function is actually a square. Right, so our thing is a square of some number, so it's always going to be greater than or equal to 0. So what does that tell us about the critical points that we found? Yeah, over here. Yeah, they're all going to be minimums. So the critical points are mins. Okay, and I want to pull up on the graphing calculator how those guys would look. Okay, so our function's graph would look something like this. It's got this kind of fold, or it's like a parabola that goes along the graph y equals negative x. Okay, so there's this parabola, right? And all the critical points lie along one line. Okay, so sometimes when our second derivative test is inconclusive, we have to work with the actual function itself a bit. Okay, are there questions there or thoughts there? Okay, very good. So this is the statements of the thing in two variables. Next lecture, we're going to do the statements in multiple variables. Okay. Oh, sorry. Yes, I hear everyone packing up. There's a short survey I want to give you. So please get out a blank piece of paper, just completely blank, and we'll fill in the survey on the back and then hand it in. Okay, so very good. Take a couple minutes and fill these out. And then on your way out the door, please take your survey and just put it here as you leave. Okay, so put it on the front desk as you leave.